In this video, we're going to derive the pullback or vector-Jacobian product rule for the solution to linear systems of equations. You can think of them as a function that takes a matrix A, let it be an n by n dimensional matrix, as well as a right-hand side vector B, and then solves implicitly for x by employing a numerical algorithm. Depending on the size and the structure of A, there are a lot of choices for numerical algorithms. You can either use direct methods like factorization-based methods with LU, Cholesky, or iterative methods like conjugate gradient, GMRes, or multicrit. Those problems are extremely fundamental to numerical linear algebra and thereby build the basis for many applications that are built on top of that. So for instance, the numerical solution to PDEs, implicit time steppers for ODEs, optimization methods, and a lot more. This is also the reason why you find a lot of algorithms in order to solve this problem, which we here want to call the Primal problem. And now imagine that your linear system solve is part of a longer chain of computations. So for instance, you have an differentiable physics simulator that simulates the solution to the Navier-Stokes equation, or more precisely the incompressible Navier-Stokes equation. Then at a certain point, you need to project your velocity field to incompressibility by solving a linear system of equations. And you do that a couple of times. And now you want to backpropagate some gradient, or better, more precisely, cotangent information through the computational chain in the reverse order. Now you need to be able to backpropagate this gradient or cotangent information over this solution or this implicit solution. And this is what we're going to derive, or we're going to derive a certain way in that video on how to do that. Let us first write down this task. So the task for the video, or generally for a pullback rule, is to backward propagate cotangent information on the output. And in our case, for the linear system solver, the output is a vector x, and we denote cotangent information with a bar on top. This one has the same shape as the primal quantity, so it is also an n-dimensional vector. And we want to backpropagate that to the inputs, and the inputs to our function are a matrix A, and let's denote its cotangent with a bar on top. This one is an n by n-dimensional vector, as well as the matrix B, which is an n-dimensional vector. Sorry, this is an n by n-dimensional matrix. Our goal here is to find a rule which applies to the numerical system solving and considering it as some sort of a super node in our computational chain. So we do not want to open the black box of the numerical solver and kind of leave that kind of solver agnostic. So we want to find a way in order to backpropagate that information without making the reverse mode AD engine accessible to the computational steps, for instance, in the LU decomposition or in the conjugate gradient. This is a valid alternative way, but oftentimes it comes with certain problems. Like for reverse mode AD, you need to tape intermediary values, so you save them. Or you might also encounter some numerical instabilities. Or even worse, your numerical solver might not be reverse mode differentiable at all. So let me highlight this. What we're going to do is something that does not require the reverse mode AD through the numerical algorithm. So without reverse mode AD, or you might also call it backpropagation. So without backpropagation through the numerical solver, pick any of the available algorithms. And this is also typically called unrolling because these have certain amounts of computational steps. The iterative methods have certain amount of iterations. And an unrolling would mean you do not consider it as one big solve, but unroll its iteration and consider the numerical algorithm as another chain of computations. So that's not what we want to do. But how can we avoid that? To do that, let us first denote the general definition of a pullback rule or a vector-Jacobian product rule, in that we backpropagate by taking the cotangent information on the output and denoting it with the bar here again, and then left multiplying it, so with a transpose, with the Jacobian of the function, so df with respect to dA. Since f is a function which takes a matrix and vector and maps it to a vector, it has a vector dimensional output. So deriving a vector with respect to a matrix, it's a bit tricky. It gives us like a rank 3 tensor. Still, if we contract over the numerator, we will still only have a matrix left, but to figure out the dimensionalities here in symbolic notation is quite tricky. Either way, this will give us the cotangent information on the matrix. And I will put this here in quotation marks. And something similar holds true for the right-hand side. So we will get the cotangent information on the right-hand side, more precisely transpose, if we take the vector x cotangent, transpose, and then with df by db, and as said, a bit loosely. Let's also note this down. Yep, this is not a nice quantity. Let's say, this is not a nice quantity. And in order to remove the ambiguity of symbolic notation, let us go into index notation. So let's write down the exact same in index notation. First, let us do the primal or the forward computation. So primal or forward, I mean, it's not necessarily a computation because it's kind of an implicit constraint. The actual computation is done by the solver, but we kind of black box the solver. So let's call it like this anyways. So the constraint is given as aij. So we take the matrix, it has rows and columns, so we need 2 indices. I arbitrarily selected I and j here, then multiply that with xj is equal to bi, and this is essentially the constraint our numerical solver is considering as part of its computation. Okay, based on that, let's inspire us and write down the pullback operations. So now the pullbacks, and here we go, that we have cotangent on A, but let's use some different indices. So let's say this is KL. So we will get the cotangent matrix. It has the same shape, but let's use different indices here by saying that we will take the cotangent on the output, here index j, and multiply it with the Jacobian. And for this, let's take the function, index it at the jth output, and derive it with respect to AKL. And here we see we use the Einstein summation convention, which is the multiplication or summation over indices that appear twice, and thereby we have a contraction with the numerator. And this is always what you see in vector-Jacobian products, because we left multiply the cotangent on the output with the Jacobian, whereas in forward mode AD you would do a Jacobian vector product, which would be a right multiplication. Okay, and let us make one trick here, or not just one trick, but it's just that helps us later on, in that we associate the function with its output. So we could equivalently write that this is bar xj multiplied with xj with respect to AKL, because xj is essentially the output of our function here. Okay, the pullback for the right-hand side vector b works similarly. Let's have the bar on top, and index k is given as xj multiplied with dfj with respect to bk. This is essentially now the general pullback, but in index notation. And in order to now find a closed form expression for this, we need to find expression for these derivatives here. So for this one as well as for this one. And since here it is a little bit easier because we are not getting a rank 3 tensor, let us do that one first and this one afterwards. Okay, so let's go with number 1, the derivative of xj with respect to bk. Okay, how can we find that? I mean, this is essentially the Jacobian of our numerical solver. That's kind of an abstract quantity, but we can make usage of a result from the implicit function theorem, which is by the help of implicit differentiation. So because we have our constraint that has to be fulfilled by a solution to the linear system is only a solution if this holds to equality. So if the matrix A, which is given, multiplied with the proposed solution is equal to the right-hand side that is given, or in numerical terms has to be approximately. Depends a little bit on your tolerance that you are able to tolerate, but in analytics it should be identical. Okay, since this has to hold, we can take that condition and implicitly derive it on both sides with respect to bk. So let's do that and say we do some implicit differentiation and take the derivative with respect to bk of aij times xj, and on the right hand side derivative with respect to bk of bi. Okay, let's do the right hand side first. If we derive bi with respect to bk, you will get the Kronecker delta ik, because this result will only be 1 if the indices match identically. And on the left hand side, we see that the derivative operator propagates to x, because a does not depend on b, so the system matrix does not depend on the right hand side, whereas quite obviously the solution to the linear system depends on the right hand side, because if you change the right hand side, you get a different solution. So what we will get is aij times dxj times bk, or with respect to bk. And this is the quantity we looked for. So this is the one we wanted to get, and we found it by implicit differentiation. So let's rearrange for it. So this means that dxj with respect to bk is aij inverse, or the inverse exists at that particular point, multiplied with the Kronecker delta. And the Kronecker delta induces an index change, changing the indices from I to k. So what we get is that this is matrix kj inverse, and it's a bit abstract here. So we found an expression for the Jacobian, which is based on the inverse matrix, so the exact inverse matrix. I mean, you should never compute the exact inverse of a matrix, or at least for general matrices. So later on, we will then left multiply it with the cotangent, and then we will see something really interesting. But before we do that, let's go on to point number 2. And point number 2 is this rank-free tensor. So it's the derivative of xj with respect to akl. It is a rank-free tensor, but we will do exactly the same. We will apply implicit differentiation on our optimality criterion, or the linear system constraint. So implicit differentiation. So let's derive the left-hand side with respect to akl, and the left-hand side was aij times xj, and the right-hand side is also derived with respect to akl, and here it was just bi. Let's do the right-hand side again first. And since the vector does not depend on the matrix, so this will turn out to 0. And here we have to apply the product rule, because obviously both the matrix depends on the matrix, it's the identity in some form, but also the solution vector x depends on the matrix, because if we changed the matrix, we would have also gotten a different solution. Okay, let's do the component first of deriving aij with respect to akl. So I will just write that down abstractly. So daij with respect to akl multiplied with xj plus, and then aij times dxj with respect to akl. Let's evaluate this derivative, and this will do essentially the same as with the Kronecker delta for the first one, but now we will get two Kronecker deltas. So we will get delta ik and delta jl times xj plus aij times dxj with respect to akl is equal to 0. Let's rearrange that for the quantity we are interested in. So we will rearrange and see dxj with respect to akl is, and crucially, minus aij inverse times delta ik times delta jl times xj. And let's also apply the Kronecker deltas here, but we have to be careful that they can only be used once, so they will only make one index change here. So we will get here a change from I to k. I want to do the change here on I on the matrix, so we get kj inverse, and then let's change the index here and we will get an xl. So we will see that the result of the differentiation, our rank-free tensor, is given as something really absurd. So this is a computation that is probably quite hard to express in symbolic notation, but you never have to do it. So the essential idea of vector-Jacobian products, and equivalently also Jacobian vector products, is that you do not build the full Jacobian, or in our case, this rank-free matrix, but you left multiply it with the cotangent. And as such, we will then, here it is, and as such, we will then reduce again to a matrix. So we will never have to deal with the headache of rank-free tensors, at least in the particular scenario we will look at here. So this is the quantity we want. I will just note that down again. So this is dxj with respect to akl. So let's use the results we got and plug them back into our general pullback definition. So let's plug back in, and then we will first get, let's do the right-hand side again first. So the b index k cotangent is cotangent xj times dxj with respect to bk. Let's plug in the result we got, which was that one here. So it is xj times a inverse index kj. We can rearrange that and move the inverse back to the left side and see this is a kj times bk is cotangent xj. So cotangent xj is given, cotangent bk is what we want, and we will soon see we will have another linear system of equations, but I think this is more clear in symbolic notation. So let's leave that for a second and go back to the second point and have the cotangent index KL of the matrix A is minus xj cotangent times A inverse kj times xl. And here we will see now we have the contraction over J, and thereby we go back to a rank 2 tensor, a matrix. Isn't that beautiful? So we just needed it as kind of an intermediary tool, but due to the beauty of vector-Jacobian products or pullbacks, we never have to deal with the full Jacobian. I think that's an interesting insight. Something interesting to observe here is that the multiplication of cotangent xj with A inverse kj is essentially the cotangent on the right-hand side. So this one is cotangent bk. And as such, we will get minus cotangent bk times xl. I will explain that in a second, don't worry. And what we see here is essentially the outer product of two matrices. So you will get the cotangent on our matrix as an outer product. Okay, let's make this more clear by going to symbolic notation. So back to symbolic notation. So in other words, matrices and vectors. And for this, we will see that bk is given as the solution to a linear system of equations. And I just want to make this a little bit more verbose and kind of adhere to the general notation you see in pullbacks or adjoint problems, in that you, instead of solving for bk cotangent, you solve for an adjoint variable. And let's denote that lambda. And say lambda, or vector lambda, is given as the solution to A times lambda is x cotangent for lambda. But wait a second. This is not what our index notation showed us. Because take a clear look. You have A index kj times bk equals xj. And let's look at the primal problem. And the primal problem was aij xj. So the rightmost index of the matrix is the index of the unknown vector that we solve for. But here it is not. Here the index that matches the unknown vector is the first one. So we are using the transposed system matrix. So we kind of have a transposed linear system of equations. It's the same matrix. It's again the primal matrix, but then we saw, I just used that as kind of a placeholder. We see that the cotangent on vector B is essentially the adjoint variable. And maybe let me also give that a name here. So lambda is the adjoint variable, and the adjoint variable has the same shape as the primal variable or the primal output. So it is another n-dimensional vector, which will also be quite obvious since we will get the cotangent on the right-hand side. Okay, finally, we can then denote the cotangent on the matrix. And here we saw it is an outer product. Now I also want to use here the adjoint variable. So this is the adjoint variable. Don't forget the minus, multiplied with x transpose. And x is the solution from the primal pass. So this is the original output. And here we again see how intertwined automatic differentiation or reverse passes, but also forward passes are with respect to their primal computations. So this is an outer product. And obviously, we will need an outer product because what other way is there to go from two vectors to a matrix? We have to blow up. We have to kind of outerly multiply it. And this brings us to the full pullback rule, So we backward propagate cotangent information over the function f, the solution to the linear system, which has the primal inputs a and b, as well as a cotangent on the output denoted as x bar, in that we first solve the primal problem, so call the function f on a and b, and this will give us the vector x, the primal output x, for which we have a cotangent counterpart, and then we will first find the cotangent on the output as lambda, so this is b bar, and we will find the cotangent on the matrix as minus lambda times x transpose. So this is the cotangent on the matrix. And again, we will need the solution to a linear system of equations. So this lambda appears in 2 points. It appears here, and it also appears here. And also important, we will see the primal solution also appearing here in our outer product. And I want to highlight this a little bit in writing it down a different note, so we can have an alternative way of spelling that out. So we say alternatively. We could also have the pullback on f with primal input a and b, as well as cotangent output x, given as the solution to the linear system, the primal linear system, and I'm kind of using a hypothetical inverse matrix here. And then we backward propagate cotangent information by solving a to the minus transpose on x. So we will solve a linear system, but with the transpose matrix. And this one gives us b cotangent. Well, this one gave us the primal x. And then the cotangent on the matrix is minus b cotangent times x transpose. So it will take that one here as well as this one here and close them up into our cotangent matrix. And that is an alternative way of writing down. Generally, we will have a similar insight as in the push forward. We will need the solution to another linear system of equations, which involves the system matrix as from the primal pass, but in the transpose way. So this is the crucial insight. It requires, in either way, either in that form, because there we had it with the lambda, or more verbose in that case, requires another linear system of equations or another linear system solve, and then importantly, but with the transposed primal matrix. So this will be the matrix A transpose, and it's another n by n dimensional matrix. 2 remarks here. So we said that there are 2 primary categories of numerical solvers. There are direct methods and there are iterative methods. We can kind of reuse information from the primal pass. So if we used an LU decomposition, for instance, to solve the primal system, we can just transpose the LU decomposition and then solve the auxiliary system for the backward parse by just a backward and a forward substitution. And as with all factorization methods, typically the computational cost of the factorization scales cubically, but of the subsequent solve is just quadratically. So which actually makes this additional solve really cheap if you have access to the adjoint factorization. So let me note this down. So if primal pass was done with direct solver, we could reuse its factorization in the adjoint form. And if we did the iterative solver, we most likely used a preconditioner, especially if we have really large PDE systems. And we can also use the adjoint form of the preconditioner if applicable. It's a little bit more tricky there, but it's also an option. So, or use adjoint form of preconditioner if applicable, of course. That's a little bit problem dependent for an iterative adjoint solve. And there's one last remark I want to do is that the cotangent on the system matrix is given by an outer product. And that is kind of a bit complicated or something you have to wrap your head around, because in a lot of cases where your system matrix from the primal pass is sparse, this will not be sparse. So let me note this down. This is not sparse. And that's an issue. If you solve PDE systems with matrices being 1,000,000 and 1,000,000, but they're sparse, there are only a couple of entries in there, this one will then be a dense 1,000,000 by 1,000,000 matrix. And typically this exceeds your memory, and also it's a lot of computation one has to do. An alternative would be to use sparse outer products. So we need sparse outer products because obviously the structure or the sparsity pattern of the adjoint matrix has to match the sparsity pattern of the primal matrix. So we only need to do an outer product at those points where the matrix A is non-zero. And it also becomes a bit more difficult if the matrix A is given matrix free. Then it kind of becomes a little bit bigger headache in how to backpropagate through the matrix assembly path or through the particular matrix-free implementation. But I will leave that open since this is a really advanced topic, and generally for small linear systems you can be fine with an outer product. In summary, once again, we wanted to do a backpropagation or a pullback over the solution to a linear system of equations as part of the numerical solution of PDEs, incompressibility projection in Navier-Stokes method, optimization methods, or in nonlinear solvers, you name it. In order to do so, we will solve another linear system, but with the transpose matrix for an adjoint variable, which turns out to be the cotangent on the right-hand side, and we will build the cotangent on the system matrix using an outer product, which is quite an interesting insight because you will also see that this outer product appears in a pullback for a matrix vector product. If you're interested in that, I have the derivation video linked up here. A big thanks to all the patrons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you will find the link to the Patreon page down in the video description. I hope you enjoyed that video and it was helpful to you. Please feel free to leave a like and consider subscribing to the channel. There is more awesome content on reverse mode rules, or more generally, reverse mode automatic differentiation, which I still think is an amazing insight into numerical mathematics, that this works and is part of so many applications, most famously, of course, deep learning. You will find videos on that. And with this, I hope to see you in one of the next videos.